Welcome to the place where we gain knowledge through the lens of creativity. I am Aaron Dworkin, and this is Artful Science. Thanks again for joining me here on Artful Science. Today's show is comets, and our guest is Anita Cochran, who serves as Senior Research Scientist and Assistant Director of the McDonald Observatory at the University of Texas at Austin. Anita, welcome to the show.
Thank you.
And of course, we're very excited. This show is co-curated with our wonderful thought partner, NASA. And so, Anita, I thought I would just really delve right in. I'm, fascinated with comets, as I think many people are, but don't actually know that much about it. So first things first, because I hear comets and asteroids, is there actually any difference between a comet and an asteroid? And if so, what is that?
For the most part, the difference is how much rock there is in something versus how much ice there is in something. When the solar system formed, the regions closer to the sun were warmer, so you couldn't keep ice around, and most of the gases boil off. And so things that formed in the inner solar system are more rocky, and things that were more in the outer solar system have more ices in them. So the comets and the asteroids both are leftovers from the formation of the solar system, and they're the building blocks of various objects. And so, for instance, Jupiter got formed, for the most part, out of things that were more icy because it's out past where ices can stay. And so we consider the comets to be dirty snowballs or icy mud balls, or it's about the same mass of ice and dust. And when astronomers talk about dust, what they mean is really just dirt, the same stuff you have on the ground. And when we talk about ice, we don't mean just water ice, because although comets are about 80% water ice, the other 20% are things like methane, ammonia, formaldehyde, carbon dioxide, carbon monoxide, methyl alcohol, all sorts of things. But as I say, 80% of it is water by mass.
Gotcha. And so comets, is there an actual threshold, or basically comets are kind of mostly water and asteroids are mostly, dirt, if you will? How is there a threshold?
Well, we use a sort of morphological definition. So if you see the comet have a coma, which is the fuzzy part that comes out around the nucleus, we call that a comet. So there are things that are in the asteroid belt that do actually have comas. And so some people refer to them as active asteroids. Other people refer to them as, main belt comets. It's a little ambiguous which they are. Really what you want to know is how do they form and where did they form, but you can't tell that necessarily. They don't come with instructions.
Gotcha. And of course, asteroids basically don't have that trail behind them.
That is correct. Most of them don't. Because
there isn't the actual water that's, I guess, evaporating off of them?
Yeah, it's what we call sublimation or subliming. If you would take an ice cube and put it on your desk in your office, you'd get a puddle. But because you take that ice cube and you put it out in space where it's essentially a vacuum, it actually changes directly from the ice form into the gas form. And that's a process called sublimation. And so that's what we see them undergo. And that's why we see the gas, and the gas takes some of the dust and carries it off with it.
Gotcha. Well, that is awesome. And this is why I love this show so much. I've already learned more about comets than I've known most of my life. So in terms of comets, how you mentioned that, a lot of these, form, much earlier on in the history of the solar system.
That is correct.
How do they actually form? So how do comets actually form?
Well, you go back to the first question of how does the solar system form? And basically you have clouds of molecular gas and dust, and nothing sits still in the universe. So they're swirling around, and eventually something gets an increase in density, and that causes things to start gathering, because gravity is a rather important force. And because things are moving, they're going to spin. And like you would have a figure skater spin, and depending on whether their arms were in or out is how fast they spin. That's angular momentum, and you get a disk out of the material. Or it's like throwing up a pizza, any of those things which cause things to move outward. So you get the star forming, and you have this disk of gas and dust, and it's in the disk of gas and dust, you get, again, gravity coming and getting what we call planetesimals, which are comets, basically.
Gotcha. And so in that kind of process, is it the forming of the process of a planet or of a star itself that kind of shoots off these comets?
Well, the material, the stars it's forming, it's collapsing, it's building up pressure, and eventually gets to the point where it's got enough pressure that it gets warm in there, actually very warm in there, 1,000,000 degrees. And that starts to push material out. That's the first thing that starts to clear the disk. But also as the planets grow, they start gobbling up more material. They also start influencing it gravitationally. So they'll push and pull it depending on where they are in their orbits. And sometimes that changes the orbit enough that it ejects the comets or any of the debris from the solar system. So about 90% of the material is lost, but the other 10% is still part of the solar system today. It's not where it probably formed in the first place. Most of the comets now live very far from the sun and only occasionally come in. And they were formed basically where the giant planets are today.
Gotcha. Fascinating stuff. So switching gears a little bit, thinking about comet impacts, those types of things. And of course, I remember it was so big in the news, Shoemaker-Levy 9, when it collided with Jupiter. This is now 30 years ago. I can't even believe, because I have such a vibrant memory of it. Did we learn anything by observing it because it was such a significant event?
Where we learned was more about Jupiter than we learned about the comets. We did know the comets were very porous and very, very fluffy, and they could come apart very easily. So gravity can pull them apart, although they fall apart when they're nowhere near anything like Jupiter. But what happened is when it pulled it apart and they had this long train of objects, many of those hit Jupiter, and they left a signature in the atmosphere of Jupiter. So it told us something about the way the atmosphere of Jupiter worked. We also realized that on the satellites of Jupiter, we oftentimes see a ring of, not a ring, but a line of craters. And we hadn't ever really known for sure what caused that. Well, if you pull apart something like a comet close to the satellite, it's going to leave bang, 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 a whole line of craters. And so those kinds of things we confirmed. Now, we did learn some about the comet, but mostly what we learned about was Jupiter itself.
Gotcha. And so have we actually seen that, where we see that string on Jupiter like that we see that on Earth, where we see a series of comets, so we know something has come and broken up in that way here?
We don't actually see it on the Earth because the Earth has been so resurfaced. So we don't know that many craters that are left. And where we see it is not on Jupiter, because Jupiter doesn't have a solid surface, but on some of the satellites. And they are not as resurfaced for the most part. Io certainly is, but some of them are not, like Callisto or Ganymede, are not as resurfaced. So we do see this kind of train. We see them sometimes on the moon. So, we realize it's a process that happens, but we didn't have an explanation before this. And this looks like a plausible explanation.
Gotcha. So, everyone wonders if we love making massive movies about massive impacts with the Earth, comet strikes, etc. So just wondering, does it happen frequently, actual comet strikes? And do we have any sense of the odds of a significant impact in the future?
Well, the big things don't happen very often at all. The last sort of large thing, and that's really more big boulder or small mountain size, was in 1908 in the Tunguska region of Russia, where where an object that we're almost positive had to have been a comet came in, and it actually didn't hit the Earth. It actually broke apart about a few kilometers above the surface of the Earth, and it had a huge airburst of pressure. So it knocked down trees for like 50 miles around. We know things hit the Earth all the time. Basically, right now, we're being bombarded by little tiny particles. They don't mean anything because they don't get through the Earth's atmosphere. It's useful having an atmosphere. But the bigger things that come through, most of them that we know about what they are from pieces of asteroid. And the reason is because that being more rocky, it's harder, so it makes it through the atmosphere better. So the comet stuff doesn't make it as far in. It doesn't mean it can't come in. And one of the things that's different between comets and asteroids is because of the changing of the orbits when they formed, and the comets can come from any direction. And if they're coming opposite the orbit of the Earth around the sun, then they have more velocity. And since the energy is the mass times the velocity squared, it's coming at you faster, it's more of an impact. So you have this combination of maybe potentially higher impact velocities, but lower porosities, or lower strength. And so, they balance off. And we tend to have more strikes of more rocky bodies, but even those are fairly rare if you get into the sizes that would be a lot of damage. Of course, we do know that the dinosaurs were killed off by an impact, but that was an asteroid.
Gotcha. And if we, if God forbid that we actually saw that and there was either a comet coming, in the wrong direction that was significant enough, or simply a large asteroid, again, could we?
What do we do?
Right. What would we do?
Well, the whole thing is to find it as far out as possible. If you're going to change the orbit so it doesn't hit the Earth, you want to do it as far away from the Earth as possible, because a small tweak is more important out far than it would be in close. Now, you're not always going to find it far out. So the next thing you got to say is, well, what do you want to do with it? The worst thing you could probably do is to split it up into lots of pieces, because then we have to duck lots of pieces. So what you want to do is you want to push it to change their orbit. So you want to maybe set off an explosion on one side of it, presumably the Earth side, to push it out. And as I say, the further away from the Earth you are, the smaller the perturbation you need to make it clear. The problem is it's a political question of what do you do? It's not a scientific or a technical question. So, if you're going to start putting off bombs and saying it's because there's this asteroid coming, you better be sure that you know that the asteroid's really coming.
Right. That's for sure. Wow. Well, it really is amazing. And I've learned so much more. Unfortunately, we're just about out of time, but I always like to ask all my guests, do you have, since we're here at this intersection of the arts and sciences, do you have any arts practices that you either practice yourself or just disciplines that you love to appreciate?
Well, I'm a big fan of music and dance and things like that. I also am a big fan of cooking, so I do a lot of cooking, which this pandemic's been good for that. But I'm not a particularly artistic person. I do like to enjoy other people doing art, and go to shows and go to concerts and stuff like that.
Awesome. Well, that sounds great. Any favorite genre for music at all, or a wide variety?
It's a variety. I like classical, I like blues, I like folk. Cool. Despite the fact that I live in Texas, I'm not particularly into country music, but I'll listen to some of it. Not into top 40 or anything like that. And I absolutely adore going to ballet or things like that.
That is wonderful. Well, Anita Cochran, thank you for helping us gain knowledge through the lens of creativity here on Artful Science.
You're welcome.